This is the video for interchange routines. Here a routine starts here on the left and ends up over here on the right. The routine starts out by setting control register N to 13. That's because there's going to be 13 values in the gray data for each one of the possible offsets. So that is needed by this add list instruction here. It needs to know the value of this control register, so it knows how many values there are at this offset in gray data. Then it says set the best trial to 0, the best value to 0. That means it hasn't found anything yet. Then it sets significant bit to 0. That's going to be used down here when we change the gray code bits into binary bits. Next, it takes the sum of the 4 values at gray start, offset 1, and puts it into gray start. Well, the first one is the value of that change, and the value is always the 4 values at offset 1 in that particular one. Down here we show in a previous routine it had said that all sum gray data 1 from I and put that sum at gray data I. That's the value of that particular solution. Also has to do it at the offset 1000 because it has to do with whether it's coming into the solution or going out of the solution. Well, here it sets, well, first we'll say for I of 1, all the way down to I goes the value of trials one at a time. It's going to go around here for every one of the trials. First, it needs to set J to the offset I. That's going to tell it which one is coming in or going out of the solution. And then here, the gray data for that particular, the Jth one, is going to be added to the gray values. That's wherever the values are at that time. And the very first gray value is actually going to be the value of this solution. So the next thing it says, branch if less than or equal gray values to the best value, go to CE. Well, that's down here. Goes to the next trial then. But if it's possibly a better solution, it still has to check to make sure that the values in gray value are acceptable. That is, first of all, for k equals 1 to k of 8, it checks to see if the gray value at that offset k is more than the maximum train cars that are allowed. If it is, it goes to CE again. It's not an acceptable solution. It also, for k of 9 to k of 12, it checks to see that the gray values there aren't greater than the maximum siding cars. How many cars can be on a siding? If it's greater, it goes to CE again. Not a valid solution. But if it is a valid solution, it saves the value of I in the best trial. And it also says now the best value I found is the gray values. So there it knows which one was the best. It saves its value and what its gray value is. And then it says move the 13 values from gray values to save data. It's just doing that to check out the program. We're not going to see save data being used. Well, once it goes around here, the number of trials times, it knows where the best trial is, and its value is in I. That's what its offset was at when it was the best value. So now we got to take that value, I, and convert it into its individual bits. But they're going to be stored as values 0 or 1. Well, here it sets V equal to the best trial. That's what we saved up here, the best one. Then it says set result bits plus I to that value of V. Then it says take that value and divide it by 2 and keep the remainder in result bits. Well, it's going to be a 0 or a 1. So it's finding out which bits are on in our gray code value. Then it says divide V by 2. So get rid of that first one. Now we're going to go to the next one. But each time we do find one, we remember its value, significant bit I. Then we branch if V is equal to 0 to CH. Well, eventually it's going to be 0 because it's not possibly going to be 20 bits in that value that we saved up here, since that value only goes to 4096. That's the value of trials. So it's never going to go 20 times. So eventually, though, V is going to be 0. Keeps dividing it by 2. It runs out of positions. Well, so eventually we get over here to CH. And here it says put the significant bit into U. That's where it's going to start with its binary positions. That's the highest offset for the binary positions. But it fills the 20 of them with 0. These are going to be where the binary bits are going to be put at gray bits. Then it says, well, set that gray bit at offset U to 1. It's the most significant one, and when you're converting to binary from gray code, the first significant bit is on. Then it subtracts 1 from U. That's the index it's using for gray bits. It sets gray bits at that U to result bits at 1U. Adds to it the result bit at U. This is how you convert the gray code bits to binary bits. You have to add 2 of them together. Then when you add the 2 together, it says, well, now take the remainder after dividing it by 2. Then go back to CJ again. And until U, you subtract 1 from U, and then until U becomes less than 0, we go around again. When it's less than 0, we go to CK. At CK, it moves the 12 values at list A plus 70 to item offset. Well, down here, I show you what's at list A plus 70, 3, 5, 7, 9, 13. It's going to be used for indexes in this answer pick. Well, it sets J, well, it's going to go around here for I of 0, down to 11, and it's going to set J to that item offset at I. So the first time it'll be this 3. Then it sets answer pick at that offset 3 to 0, but then it says branch if equal the gray bits of I to 0 to CN. That means the bit wasn't on. But if the bit was on, it says set the answer pick at offset J to 1. So when this is finally done, answer picks here is going to have the values of all the ones in the answer. Alright, this is the end of the video on interchange routines.